is Jordan Caraballo-Vega, who is a PhD student from University of Maryland, College Park, and also a computer engineer from NASA Gather. And his presentation today is titled "Towards an Operational Cloud-to-Ground Lightning Probability Model for the Alaskan Tundra using Machine Learning and the Weather Research and Forecast Model." All right, Jordan, it's all yours.
Can you actually see my screen?
Yes.
Nice. Okay. Hello, everyone. Thank you very much for being here. Uh, I'm gonna present some of the work that I've been doing for my PhD. I'm actually finished my first year working with Dr. Tatiana Loboda. I also work with Dr. Mark Curl at the Goddard Space Flight Center, particularly like the data science group. So I do a lot of high performance computing, just trying to accelerate some of the modeling we have and some of the actual remote sensing processing we do at Center. I'm actually focusing for my PhD in the Alaskan tundra, particularly working with fire. And this is kind of the first step of that, I guess, long road of the PhD route. Just to provide a bit background about myself, I'm actually from Puerto Rico, like southeast side of the Iceland. So I'm just kind of presenting myself formally for to the team. For some of you know me, but I think I haven't met formally many of you. So nice to meet you all. Uh, Main idea is that we know wildland fires are just causing dramatic changes, and they have been relatively rare in the Alaskan tundra. Like when if we compare it to like the boreal regions, but they still release a vast amount of below carbon stores, permafrost, and many other um, biophysical and biological interactions that happen in tundra. So we need to understand them. We need to understand some of these processes are happening that are affecting many of the decisions and many of the actual dynamics that are occurring and that provide some value to the climate warming as well. References say that there's going to be a future increase in the frequency, but also in the extent of some of the wildfires. So we kind of need to understand the end-to-end process of these, and some of these rapid rates of warming and some of the actual like changes in precipitation, they have just been increasing some of these, and they have been influential to the actual dynamics that happened or that are happening right now in the Arctic tundra. uh, Cloud to around lightning is actually one of the main sources of wildfires in the at least ignition wise in the Arctic tundra, and this is because of that limited human activities and so forth. So we need to understand how lightning actually affects and how lightning influences some of these dynamics. But besides lightning, then we also want to kind of understand what are the factors that are causing some of these increases in lightning that are occurring over the past couple of years. Right now, we're seeing kind of this huge trend having, let's say, June and July as those really active lightning months. So we want to understand what is different between, let's say, those early months to the other ones, and how those interactions are actually changing some of the dynamics um, in the tundra. Now, we do have challenges. So in the tundra, we don't have enough sensors. Right? We don't have all of the sensors that we may have in other locations of Alaska. So we need to kind of work our ways around that lack of data to then try to improve our understanding of the area. Another challenge that we have is that we still do not understand strictly how what are the dynamics that are happening. We do have many projects that are, let's say, concentrating the boreal because many of the most of the fire activity is actually happening along those areas, but uh, we need to understand why this tree-less environment is just burning and is just uh, increasing wildfires across the year. So what are the objectives of this work? Well, as I told you, this is kind of the first stage or a long-term project, but the first goal in here is to kind of demonstrate the potential of combining this physics-based modeling to with data-driven machine learning in a location that we're just data scarce. We don't have a lot of data, at least in the climate side of things. We also want to identify some of these factors that are then affecting cloud-to-ground lightning probability in the tundra, particularly to look at lightning and then to model what ignition is happening and how ignition is uh, being influenced by some of these climate conditions. And the last goal is to actually determine some of those meteorological variables that are needed to model cloud-to-ground lightning probability across 10-day forecast. So the overall goal is that we want to model lightning, but we want to do this in an operational fashion. We have many, let's say, websites that provide WRF data or climate data, coarse resolution, but we want to kind of provide more let's say high spatial resolution climate variables that we can then work with, that we can then adapt to some of the remote sensing data sources that we normally used. So just to introduce some of the methods, uh, a previous student from our lab, which is now a doctor, actually worked on a previous attempt and a previous workflow of this um, cloud to grinding probability mapping using weather research forecasting variables to then simulate some of these lightning. And the idea was that on our data stack, we would have all of our climate variables that were simulated by WRF, and then on our prediction stack, as let's say our dependent variable, we would have lining found from the Alaska Lightning Detection Network. So it's kind of this workflow of aggregating our data stack, aggregating our lining stack, and then producing cloud to ground lining probability maps, particularly at 24 hours and then 48 hours. So in this work, we actually want to extend that. We want to move forward and then look forward to 10 days. So the first component of this is to actually simulate our climate data. And the way we simulate our climate data was actually using WRF, which for those of you that might not be familiar, is just a state-of-the-art mesoscale numerical weather prediction system. It's basically used on both research, but also on the operational side of things. And what we did is that we created a two-way nested domain. So we have a really coarse resolution domain, let's say for the wider study area, but then we have a 5 kilometer domain that then concentrates on the Alaska and then covers all of the Arctic tundra, all of the Alaskan tundra, which is our main focus in this work. Once we, let's say, model our data, what we did is that we developed this Python-based software framework, one, to set up the experiments in an automated fashion. So we don't need to be, let's say, recreating those experiments manually, but also then to extract variables that were just not available, let's say, open source or around. The other thing that we developed was this actual framework of running some of these simulations in the adapt or explore cluster where we have many of our above domain specific systems and supercomputing systems. So what we did is that we set up some of these experiments using data from the National Center for Environment Predictions as our initial boundary setup, and then simulated across 24 hours, 48 hours, and then 10-day intervals to gather all of that data stack. Once we gather our, let's say, our independent variables, then we look at our lining detection network, which provides all of that, let's say, truth or values of how lining have been progressing through time across the entire Alaska. And they have many sensors, but the idea is that their accuracy is at most 5 kilometer accuracy. So we take observations from the AODN database, and then we match them with our WRF climate variables to then have this tabular data set where we have climate variables that coincide with the specific lining occurrence observations that are being taken by the AODN. And what we did is that we kind of segregated our data set into three specific severity levels. We have a high severity level, moderate, and then low. And the idea here is that this allows us to have a better stratified sample of our data set. This allows us to both simulate on days that we do not have many lining or we just don't have any lining, to then days where we are actively receiving lining on the ground. The idea here is that once we do have, let's say, this our data set, we then start modeling at 24 hours, 4 hours, and then so on. So we have continuous predictions out of the what is the actual lining probability for this specific pixel on our study area. Um, Once we, let's say, have our data set, we then proceed to do some of the modeling. And difference from some of our previous work here, we tested both a random forest and a gradient boosted algorithm, particularly the XGBoost. And for those of you that might not be familiar with this algorithm and why we chose it, let's say, to test along the random forest, that the random forest is this decision tree algorithm that just take decisions based on particular occurrences. And you have an ensemble of all of these trees that are then taking decisions. But this is a one-step process. Once we introduce the XGBoost, then we have also an ensemble of trees, but then all of these trees are providing input to our initial iteration process to then provide, like, you have been failing on some of these observations. These are some of the input samples where just you're just not producing accurate enough observations, where you're just not matching the truth value. So the XGBoost provides that as an iterative process where then all of the trees ensembles continue to be then changed or continue to improve upon that initial iteration between both the truth and then the actual performance of our model. So once we define a model, what we do is that we select a stratified sample of all of the three severity levels and then simulate some of these cloud to ground lining probabilities across 24-hour intervals. And to have and to stack all of our data set, we selected 20 different temporal windows from 2003 to then 2022 to allow us to simulate some of those operational components that we're interested in. So I just introduced kind of the overall concept, but I kind of wanted to briefly emphasize of how the operational side of things is looking right now, because that's kind of the, say, main component of this research. Well, we simulate on the Adapt Explore cluster our WRF variables, and those are run daily, and we then simulate 10 different, 10 continuous days from that. We use 124 cores and 120 cores so we can actually simulate the word variables in just a couple of hours to then proceed to do our actual predictions with our modeling. Once we actually have our model trained, we do not need to go back and then retrain our model. So we just use the same model that we have, and then we produce the maps that we have. But we are also working on producing uncertainty maps, so we can provide both the cloud lining probability maps that we get from our models, but then also an uncertainty map. So stakeholders can look at the maps and then understand where the model is just producing uncertain predictions, just so that they can better assess some of the decisions they might take based on the maps we're producing. Once we do have all of these maps, and they can be, let's say, used for some of these science applications we have, we can actually deploy that one to a website that is being hosted on the commercial cloud. And the idea is that we can both have our data sets, let's say, locally stored, but we can also then have them available on the website for short-term downloads whenever people want to or visualize them interactively or just download the current statistics for that 10 days period of time. One of the other things that I want to kind of emphasize here is that we're monitoring the performance of our model based on the previous days ALDN observations. So whenever we reach that threshold where, let's say, our model was extremely uncertain compared to the actual truth values from the previous day, we then send alerts to via email to then say, okay, are we going to retrain based on the new observations that we have? And this is kind of a decision that we take upon us. These pieces can be automated, but we're kind of still evaluating how this would play out. And if we want to actually have this active learning being just completely autonomous, or if we want to kind of observe how, based on that threshold, if conditions are just extremely anomalous that we don't want to include in our training, or if it's worth enough to then retrain our model to look at these new conditions. Yeah. The last point from here is that we have developed containers then that can be run both on premises, so let's say on any high performance computing system, but also on the cloud. So if we need to, let's say, scale up some of our processing to the cloud, then we can do so without changing any of the actual underlying dependencies. So I just want to kind of show some of the results we have been gathering from this work. So we created this external validation data set using ALDN observations and then matching them with different WRF time windows. And we gathered close to 15,000 samples, and we saw that the XGBoost was actually providing more accurate predictions on all of the actual metrics from producer accuracy to actual user accuracy. Um, because we kind of want to understand how this would play out in operations, we also wanted to include some additional metrics for like probability of detection. How are we doing with false positives? How are we doing within our false amount rate and so forth? And then our XGBoost model was actually able uh, to supersede our random forest model as well. So we do have a pretty accurate model that we do want to kind of validate further, let's say on actual day-to-day samples that are being occurring during this summer. We also provided then an additional validation score that instead of looking at, let's say, hits or occurrence versus presence of lining, we're actually looking at how we are predicting some of these probabilities. So the Breyer score provides a metric of how distant are our probabilities from the actual, let's say, uh, absence or presence from our ground data, and how big is the error across some of those observations. Uh, these are just some kind of visual examples. This is a 48-hour forecast that we ran for the year 2005. Note that we do have some of our estimations on the higher end when we're talking about years on the previous 2005 range. But then we start matching some of the 2013 observations from high to moderate weather. uh, we wanted to kind of observe how then our model would do in periods where we didn't have enough lining during those times. So this is a kind of a forecast of a 72-hour forecast for the year 2020. Um, Same with some of the forecasting we're doing in some of the actual dates in May where we might have, let's say, warming conditions, but not enough then to have some of that convection for lining. Um, this last one is an example of the 10-day forecast that we do have right now and that we're kind of working on running operationally, where we kind of match from the moderate severity days to then a lower severity days once we're actually finishing some of that um, storm that was passing through that area. And this was actually 2022 on July. Um, the last thing that I want to mention here is that we're dealing with explainable AI to kind of understand how our model is doing the predictions. And one of the most important things here is that to actually trust a machine learning model, you need to kind of understand how the physical and biophysical patterns are affecting or influencing some of the decisions that you take. And in order to take this to the operational side of things, we need to understand what are the dynamics and what variables influence some of these decisions so we can provide trust and so that we can actually trust our model and then use them in more decision making scenarios. So what are our next steps? So we're working on the production acceptability during the summer. We want to see how our model does during the summer under real conditions, under active and live conditions. So we're trying to assess our readiness level, which right now is kind of in that 3 to 4 phase, since we have proven that based on the validation, we have some really good statistics. But then we want to see how we actually do on the operational side of things. So we're looking at day-to-day tasks. So we're gonna release the public website on this alpha version just to like look at the data, look at how our predictions are running, how the performance is in regards to the actual visualization and interaction. The other thing is we're working on improving some of our QA on certain maps because some of these machine learnings, they're sometimes they think they're certain, but they just don't provide some of that input that we need. And then the last thing is just assessing some of the correlations on the science side of things. How are lining dynamics coinciding with some of the actual dynamics that are happening on the Arctic tundra? So just to close the loop, we have proven that we have a strong capability in regards to this WRF plus uh, lining conditions. We have promising performance from 24 to 10 days, forecasting that we want to test further in operational fashion, and then combining some of this physics-based modeling with data-driven machine learning is a promising way of, let's say, overcompensating some of these data scarce regions where we might need some help getting more data from. So thank you very much for listening.
Thank you so much, Jordan. Questions? Jin?
Hi, Jordan. That was a very interesting talk. Thank you. So I guess like since this is mostly focused in the Alaska tundra, can like this model be like translated to other regions in like Alaska, for example, like in the boreal forests, or is it just are you just trying to focus on Alaska tundra for like the future and stuff like that?
So the initial priority was the Alaskan tundra because we're doing some of our work there, but we do have some plans to test on the overall Alaskan region during the summer, just to see how the model would play. I want to see if we might be able to have a single model for, let's say, the entire Alaskan region, or if we need to have like localized model just because the dynamics are just extremely different. So it's actually on the plans, and we're gonna see how that plays out.
Okay, awesome. Thank you.
Adrian? I guess that's you, iPhone.
Yeah, that's me. Sorry, I had to pick up my kids, but their last day of school. That was great, Jordan. Really excellent talk and really interesting results. Um, I was wondering about your thoughts about the importance of latent factors and how your machine learning model deals with latent factors that may be influencing the lightning strikes, but not incorporated in your model.
So that is an interesting question. So part of the idea of this machine learning model, if they don't see it, they're not going to be able to, let's say, predict it or work on it. Now, our main goal is that we're trying to get some of these climate variables to be kind of the main influentials of it, and that's why we're, instead of predicting the actual hits, like really the actual hits, we're kind of predicting that probability. And I think that would kind of play out in the actual probabilities that might influence then the machine learning model. But I don't know. As of now, I don't think we have a way of testing against it, or testing its influence on the actual machine learning model.
Okay. Any other questions? Joshua?
Yeah, so I think I learned a lot during this talk, and but a lot of the stuff's very new to me. So in terms of the explainable AI, is the information you're getting from that mainly just looking at what factors are driving your improvements in accuracy with your model, or are they actually giving you information about functional relationships that actually could be used to improve the like WRF's model itself? It's something that could to say, hey, there's actually a really there's an additional relationship between these variables that could be then introduced into the actual calculation of the what WRF is doing. Like, can you help it can it actually help you notice new things that could be improve the science inside the model or not?
So the explainable AI, it provides input on both components, but not on the WARF side of things. So it provides input on what are the dynamics on the environment, not just like looking at accuracy on the model, but what are the actual parameters that might correlate from the WARF output. Now, we are trusting the WARF simulations and using them as our kind of like base truth from the data side of things. So I do not think we have the ability from this model in particular to then influence some of those WARF dynamics. Now, we do have plans to compare against the raw like sensors, and that might actually be able to kind of correlate our output from the machine learning with some of the actual sensor data that then can inform some of the WRF inputs that we're getting. Because right now, so we don't have many sensors on the areas that we're looking at. But if we expanded them to some of the other Alaskan regions, we might be able to use more of the raw sensors to then look at how the WRF, let's say physics parameters, or even the actual simulation components can be influenced or are just being not properly, let's say, simulated. The I guess last thing that I want to mention here is that the explainable AI can be used again for the science side of things, but then also to kind of understand what are the bias that some of these data sets have. We might be able to do find like some trends that could be happening on WARF that were unexpected, that then could kind of let us know that, okay, so data from WARF is maybe not the highest quality on some of these locations, which unfortunately they're missing uncertainty. Like they don't provide some uncertainty layers that we would want, because that would make our life a lot easier. Like we wouldn't be trusting blindly some of these WARF components, but they do not. So that's why the psi comes into play.
Thank you. And if you have an answer to this that's very quick, do you know how much it costs to have a lightning sensor? Because I know there's probably other people on this call who know people who have meteorological towers in the Arctic, if not Alaska. So do you know how much it takes to add that to your meteorological rig?
I have no idea. I may need to rely on all of the experts that are in this call.
Thank you.
All right. Thank you so much, Jordan. All right. I wanna we're out of time, so I wanna thank once again Jordan and UF for your awesome talks. Yeah, thank you. And I don't really have anything else to add, except the fact that there will be a joint working group meeting next